Hello everyone, welcome to Module 5.3, Percent Composition. The learning objective for this module, calculate the percent composition from the empirical formula of a compound and vice versa. This will be a somewhat longer module. We have a couple examples here, just the math involved in the questions we see here will be a little bit more tedious. There will be several steps, and so it will be a little bit longer, so make sure you have the time prepared to go through all of this. We're going to start with a definition. The mass percent composition is defined as the percent of an element in the total mass of a compound. So when we use the word percent composition, we are referring to a percent by mass. So here we have a kind of a general formula. So the mass percentage of X, where X is any element, is the mass of X in a compound divided by the total mass of that compound, then times 100%. So I want to go through an example of this. This first example, I'll go ahead and talk about it, but I'm not going to do this by hand. However, if you would like to do it yourself, feel free to pause the recording and go through each step as necessary. So the question is, what is the percent composition of each element in lactic acid? And I'm giving you the formula for lactic acid, C3H6O3. I would not expect you to know this formula just from the name. Okay, so if you have an organic compound like this, you would be provided with the formula. So don't be concerned with knowing how to know what the formula is for lactic acid. Just look at the formula and go from there. Okay, so this is the empirical formula, and we're going to be using this information to figure out the percent composition, in this case, of each element. In some cases, you might be asked for a specific element, so maybe carbon or hydrogen or oxygen. In this case, we're looking for each of them. Okay, so first thing we do is we determine the total mass of each element, as well as the molar mass of the formula as a whole. So we're showing these steps, so this should not be new. We saw this in the last section, in section 5.2. It was set up a little bit differently, but the same idea applies. You're taking the number of carbons in the formula times the molar mass of carbon to get the total mass of carbon. Same thing for hydrogen, same thing for oxygen. And then we add these all together. Now, some of you may have gotten used to, in the previous section, doing this in a way where maybe you didn't keep track of each of these numbers. So maybe you're just looking for this number. What we're doing now, we need to keep track of these numbers as well. Okay, so you want to set it up in this way where you have a total mass of carbon, total mass of hydrogen, total mass of oxygen, and then you add them all together to get the total mass of everything. Second thing we do is we divide the total mass of each element by the molar mass. So go ahead and do that, and this is what you'll get. So for carbon, we take the total of carbon, so 36.03, divided by the molar mass of 90.08. Times 100%, we get 40% carbon. Same thing for hydrogen. Take its total mass of hydrogen divided by the molar mass times 100% to get 6.7%. And then oxygen, we take the total mass of oxygen divided by the molar mass times 100% to get about 53.29%. One thing I'll mention, again, I talked about this earlier, but specifically for this type of question with the significant figures, go ahead and use 2 decimal places. We're showing 4 for the hydrogen, and that's probably actually good for hydrogen so that you do have at least 4 significant figures. So we're showing 3 decimal places to get 4 significant figures to match these other ones. But 4 significant figures is usually what we want for these answers. So make sure to go out at least that far when you're doing these calculations. So these are the answers. Now, before we just say we're done, we can check our answer to make sure we're on the right track. And to do that, we take all of these up, add them up. They should add up to 100%. So if you add these all together, you'll get a number very close to 100%. Now, if you get, for example, I think in this case we might get 99.99%. That is close enough. But if you're getting, something like 90% or less, I would even say 90. If you're getting less than 99%, then something went wrong, and you want to go back and double check things. You can be fairly confident that you're on the right track if you do get these to add up to 100%, unless you're doing something where you are incorrectly calculating the molar mass. Okay, so these numbers do seem sensible. Another thing to look for, hydrogen is very small compared to the other elements, so we would often expect this to be a very, very small number. We have the same amount of oxygen as carbon in the formula, but the oxygen mass is a little bit larger. That makes sense because oxygen has a somewhat larger molar mass. So this is how we convert from the empirical formula to the percent composition. We also want to be able to do the opposite of this, to be able to go from the percent composition to the empirical formula. So just a reminder, the empirical formula is the smallest whole number ratio of each type of atom in a compound. So when we show the empirical formula, that's what we're showing. Actually, to be, I want to go back and look at something here. This is not actually an empirical formula. This is what we call a molecular formula. The empirical formula would be CH2O. So just be clear that that's not what we were doing in that case. So we would, when we do this method, we'll be finding we wouldn't, let's say we were going backwards from our results for the lactic acid. So maybe we had these numbers and we were trying to come up with this number. We would actually not come up with this number. We would come up with CH2O as the empirical formula. That last step of coming up with the molecular formula will be the subject of the next section, so 5.4. This is the more useful of these two. So going from percent composition to empirical formula, because this is something you would do with results in a laboratory. In fact, we will be doing this. We will be taking percent composition and using it to find an empirical formula. So there are a couple of steps here. So I want to, instead of first just jumping into an example, I want to talk about each of these steps. They're not as intuitive as going in the other direction. So I want to talk about them first, and then we'll go through an example. So you'll, hopefully when we do this, you'll understand the steps you're taking before looking at the example. So first thing is calculate moles of each element. So if you're given a percentage, assume you have 100 grams. So you take 100 grams and then take whatever percent you have, convert that to moles for each of the element. If you're given masses, sometimes you'll have numbers in masses. Just go straight to moles for each of them. So you're doing this for each element in the formula. Once you've done that, you'll have a series of moles. So you'll have moles of element A, moles of element B, etc. Whichever one of those numbers is the smallest, you'll take that one and divide each one of them by that number. So by definition, one of them will be a 1. Whichever one is smallest will end up as a 1. And then you'll end up with some other numbers for the others. From this, you will hopefully have whole numbers from this result. And you want to use the lowest whole number ratio of moles as the subscripts in your formula. There will be cases when you do not end up with whole numbers here. We'll talk about how to do that here in a moment. But first, before we get to that, I want to look at an example. So here's our first example. Go ahead and pause your recording and see if you can solve this, and then we'll come back and go through this solution. Okay, a compound contains 7.31 grams nickel and 20.0 grams bromine. Calculate its empirical formula. So I'm going to go ahead and write these down. So 7.31 grams nickel, 20.0 grams bromine. What we're going to do next is we're going to take each of these and convert them to moles. So we have nickel. We looked this up on the periodic table, so look this up on your periodic table. 58.69 grams in 1 mole of nickel. Again, we're converting to moles, so grams on the bottom. For bromine, we have 1 mole of bromine, and that is 79.90 grams. Okay, so we do the math for each of these, and we get 0.1245 moles of nickel, and we get 0.2503 moles of bromine. One quick note here, we have 3 significant figures in our measurements. I'm showing 4 at this point. Sometimes the way the math works here, it's better to have more significant figures just to make sure you're getting what you want. So when you do this step, go ahead and take it out one more place. And we sometimes call that a guard digit, so we might just underline it to remind ourselves that it doesn't really, is not really a significant figure. But it helps with our next step if we do that. So then our next step is to divide by the smallest one. So we have 2 numbers, 0.1245 and 0.2503. The 0.1245 is the smallest of these 2, so we divide by that. So I'm going to show that here. And this one is just by definition going to be 1. It has to be 1 because we're dividing by itself. This one we would check on our calculators and we get 2.01. Okay. Now, we said we should have whole numbers here, and some of you might be thinking, well, we don't have a whole number, we have 2.01. 2.01 is close enough to 2 for us to call it a whole number. In fact, if we had at this step used 3 significant figures, we would have gotten exactly 2 there. There is going to be some experimental error in any measurements you have here. So you are going to probably be needing to round these numbers to whole numbers, especially in lab. And in this case, that's clearly close enough to say that is just 2. So then what we do, we decide the formula that is we have 1 nickel, so we have Ni. We have 2 Br, so NiBr2 is the empirical formula for this compound. Okay, so I kind of alluded to the fact that we might not always get whole numbers. So what happens when that doesn't happen? So what if after step 2, instead of getting a nice 1 and 2 as we did in that example, we get a fractional number, something that cannot clearly be rounded to a whole number, as is the case in many compounds. So what we do there is we multiply all of the subscripts by some small whole number so that we end up with whole number subscripts for each of them. You might be wondering, well, what does that mean? So here we're showing some examples. So what would you multiply by to get a whole number? So if you had a number that ends, let's start with the easiest one that ends. Let's say you end up with a 1.5. If you multiply that by a 2, you would get a whole number. If you had, let's say, a 1.33, if you multiply that by a 3, you would get a whole number. So we're showing these fractional subscripts here. Sometimes people ask if you need to memorize these numbers. Ideally, you would understand them without memorizing them. Okay, so this is essentially 1/4, so you multiply it by 4. Essentially 1/3, you multiply it by 3. Essentially 1/2, you multiply it by 2. So think of what fraction are your numbers closest to, and then what would you multiply that fraction by to get a whole number. Okay, so that's how I would talk about what to do with this. When you get to things like 0.1, you are getting close enough. I would say actually, we have 0.1 here. If you're more than 0.1, so let's say you have I guess I should say less than 0.1. Let's say you have a 1.07. That might be close enough to round down, or else you would round it up to 1.1 and then multiply by 10. Okay, so let's look at an example of this. And in fact, this example is looking at a couple of things. It's looking at what we just talked about. So that will probably be important here. And it's also looking at reaction data. So this is a reaction we will actually do in the lab. Not this specific reaction. We're not going to be using iron, but we'll be using a metal, reacting it with oxygen and forming a metal oxide. So we'll have to do this calculation because we'll be finding a mass here and a mass here. I would say take a few minutes, because we haven't talked about what to do with this yet. Take a few minutes, see if you can figure that out. If you don't figure it out, watch the first part of the video where we talk about that aspect. And then I would say at that point, when we get to the point of having, so we have a mass of iron, when we get to the point of having a mass of iron and a mass of oxygen, go ahead and pause it there and try to do the rest without watching the video, and then watch the remainder of the video at that point. Okay, so we have a 0.797 gram sample of iron reacts with oxygen to form a 1.132 gram metal oxide. What is the formula of this metal oxide? I'm going to start by writing down this information. So we have a metal oxide. Which metal is that probably going to be? Well, we know it's reacting with iron. It's probably going to be iron because we don't just change the elements from one into another. So I'm going to write this as 1.132 grams FeOX. And this is saying this is some iron oxide that we don't know exactly the formula of, but we will be trying to figure out. And then we have 0.797 grams of iron. Okay, now we know because of the conservation of mass that the amount of oxygen, so we need to know what that is. The amount of oxygen here and the amount of iron we have need to add up to this total mass of the iron oxide. So if we know the mass of the iron and we know the mass of the iron oxide, the difference between those is then going to be the mass of the oxygen. So we can go ahead and subtract here, and we can find that we have 0.335 grams of oxygen. Okay. Again, this step is not something we've looked at before, so if this is a bit confusing, feel free to go back and rewatch as you need to. But this is what we'll be doing in lab very shortly. So at this point, we have a mass of iron, we have a mass of oxygen, and from there we're going to find the formula. Okay, so we've done this already. I would recommend go ahead and pausing the video here and seeing if you can do the rest of the steps, and then watching to see if you get the same result. Okay, so for the iron, we have 1 mole of iron is 55.85 grams. Again, you should be able to find this from the periodic table. And we do the math there, we get 0.01427 moles of iron. And down here for the oxygen, we have 1 mole of oxygen is 16.00 grams. And we do the math here, we get 0.02094 moles of oxygen. And then we ask ourselves, which number is the smallest? And of these two numbers, the smallest is the 0.01427. So we divide each of these by that number. This will be, by definition, 1 for the iron. So we don't even have to type that in, right? We know it's going to be a 1. And this one, so we divide by 0.01427, and I get 1.47 moles of oxygen. Okay, that is not a whole number. We want to have a whole number. So, so what do we do there? We think about what can we multiply 1.47, what can we multiply by 1.47 to end up with a whole number. And maybe a better way of thinking of that is, what number are we close to that we could do that to? So don't try to figure out 1.47, but think about, is 1.47 close to something that can easily be turned into a whole number by multiplying by another whole number? And I would say it is very close to the number 1.5. So what would we multiply by 1.5? Maybe a 2. So times 2 times 2, we get 2 moles of iron up here. We get 3 moles of oxygen down here. Just a reminder, when you do this, whatever you're multiplying by down here, you need to multiply by up here. So you're multiplying by 2, so this becomes a whole number. But then you have to do the same thing up here, because we are still dealing with this ratio. So our formula is then going to be Fe2O3 based on these calculations. Okay, so that is the end of section 5.3. Go ahead and complete worksheet 5.3. If you do have any questions, ask them on the discussion board, and then proceed to 5.4 when you are ready.